Hey everyone. So there are a few more key concepts that we need to cover before we can move on to some of the main theorems in probability theory. Right? And so these key concepts that I want to talk about now are conditional, marginal, and joint probabilities. The definition of a conditional probability, which is usually denoted as probability of A given B, which we write with this, which we denote with this vertical bar, is the conditional probability of event A occurring given that event B occurs. All right. So, for example, when we look at voting behavior in the past election, we could think about the probability of a voter supporting Biden conditional on him or her supporting Sanders or having supported Sanders in the primary elections. And we can compute these conditional probabilities as the fraction between the joint probability and the marginal probability. In other words, the probability of A intersect B, or the probability of A and B occurring, divided by the probability of B occurring. That's equal to the probability of A conditional on B. Right? And it always helps when we think about these conditional probabilities and joint and marginal probabilities to kind of think about these Venn diagrams that I showed in some of the previous videos. And if you go through the lecture material to kind of visualize what these conditional probabilities imply by just drawing quick Venn diagrams, for example. We're going back to the Venn diagram that I show in the previous videos, right? So the probability of A intersect B is, of course, the intersection of those two event spaces of A and B, right? And so when we think about the probability of A and B happening, or the intersection of those two, when we want to compute the probability of A conditional on B, right? Of course, A and B have to happen, but we don't want to look at that space of probability of A probability of A intersect B relative to the entire sample space, but we want to look at it relative to the probability of relative to event B happening, right? So in other words, we look at the intersection between A and B, but we don't look at the intersection between A and B relative to the entire sample space, but rather relative to the B event space, okay? And that's what is described as this fraction, or dividing the probability of A intersect B divided by the probability of B, okay? The next important kind of result that directly follows from the concept of conditional probability is the multiplication rule. And you can basically derive this rule by directly multiplying the probability of B on both sides of this equation. And what we get is a formula for the probability of A intersect B, so the probability of A and B occurring, which is equal to the probability of A conditional on B times the probability of B. We could also turn this around. It is equal to the probability of B conditional on A times the probability of A, right? So the probability of two events occurring is always the product of the probability of the conditional probability of one event occurring times the marginal probability of the event on which we have condition, right? Probability of B happened, and then conditional on B happening, we look at the probability of A, and that's the probability of A and B happening at the same time, right? And we can arrive at that by starting with B or by starting with A, essentially, okay? We also have the law of total probability, and the law of total probability basically allows us to divide up the probability of one event occurring, for example A, into basically parts parts that are parts of conditional probabilities depending on some other event happening or not happening, right? So the probability of A is equal to the sum of two separate probabilities, which are products of the probability of B happening times the probability of A conditional on B happening, plus the probability of B not happening, so that's the complement of B, times the conditional probability of A happening conditional on B not happening, right? So in other words, we're splitting up the probability of A happening into two conditional probabilities, one for B happening and one for B not happening, so to speak, okay? We can also extend the definition of conditional probability to settings with more than two types of events. So for example, if we have the intersection of A and B conditional on C, we can write this again as the joint probability divided by the marginal probability, which is just the intersection of all three events divided by C in this case. Okay. We can also do this the other way around in the sense that we condition on the intersection of two events, so probability of A conditional on B and C happening, which is again the joint probability divided by the marginal probability, which in this case is now the probability of B intersect C. And we can use the multiplication rule for both of those, for the numerator and the denominator, to simplify this to the probability of A intersect B conditional on C divided by the probability of B conditional on C. Okay. So now that we talked about conditional and marginal probabilities, we can kind of define our last key concept, which is independence. And formally, independence is defined as two events, A and B, are said to be independent if and only if the joint probability is equal to the product of the marginal probabilities. Okay. And so that means the probability of A and B happening, so A intersect B, is equal to the probability of A times the probability of B. Okay. Another way to interpret this is to say that two events are independent if knowledge of one event does not give us any additional information about the occurrence of the other event. In other words, if A and B are independent, then the probability of A conditional on B is just equal to the marginal probability of A occurring. And conversely, the probability of B conditional on A is equal to the marginal probability of B occurring irrespective of A. Okay. If we kind of take this into account and go back to our initial multiplication rule, we see here the probability of A intersect B is, we said, was equal to the probability of A conditional on B times the probability of B. If we now kind of take into account this idea of independence, then the probability of A conditional on B is equal to the probability of A occurring, and we're left with exactly this product that we saw here. So if, in other words, if the conditional probabilities are equal to the marginal probabilities, then this product holds and is equal to the probability of A intersect B. Okay. Yeah. So in essence, basically, what is key is that the knowledge of one event, whether or not it occurs, has no kind of doesn't make a difference for the probability of another event occurring, and that's when we talk about independence. Okay. Again, we can kind of extend this notion of independence to situations with more than two events. For example, we have now three events, probability of A intersect B intersect C, which is equal to the product of the three probabilities if and only if those three events are jointly independent. And then lastly, we have conditional independence, which means that we can also define the independence between two events conditional on another event, right? So even if A and B by themselves are not independent, they can be conditional independent in the sense that the probability of A intersect B conditional on C is equal to the probability of A conditional on C times the probability of B given C, right? So in that sense, the conditional probability or the conditional joint probability is equal to the product of the conditional probabilities of A and B given C. Okay. Note also that the joint independence implies pairwise independence as well as conditional independence, but the opposite is not necessarily true. Okay. All right, now we covered all kind of basic concepts in probability theory to move on to some of the important theorems. Particularly in the next video, I'm going to talk about Bayes' rule.